Hi everyone, welcome to PACE Institute of Technology and Sciences. Myself, Mr. Narasimha Rao, Assistant Professor of Physics in the Department of H&S. Now, I wish to explain about Hall effect, very important in case of semiconductors, especially Hall effect. Hall effect. Before discussing the Hall effect, what is semiconductor? Semiconductor is one of the category of three types of solids. Solids basically categorized into three types: conductors, semiconductors and insulators. Semiconductor means it has a small energy gap between conduction band and valence band in energy level diagram. Small means of the order of 1 electron volts range. There are examples for the semiconductors. They are silicon and germanium, pure semiconductors. There are two types of semiconductors: intrinsic semiconductors, extrinsic semiconductors. Pure semiconductors are called intrinsic semiconductors. Impure semiconductors, that mean to get an extra advantages in case of semiconductors, we have to dope certain impurities, then we get extrinsic semiconductors. Extrinsic semiconductors are again classified into two types. They are N-type semiconductors and P-type semiconductors. In this N-type semiconductor and P-type semiconductors, there are extra charge carriers are available. In case of N-type semiconductor, extra electrons are available when compared with holes, but in case of P-type semiconductors, extra holes are available than that of electrons. So, they have certain applications regarding this extra charge carriers. Now, let us see what is Hall effect in case of semiconductors. If you take a semiconducting slab, a material of semiconductor slab of semiconductor like this. This is the slab of semiconductor. So, in this semiconductor there are two types of charge carriers. We know very well that electrons and holes. Electrons have negative charge, holes have positive charge, but the quantity of the value of the charge, the magnitude of the charge is equal, the sign opposite. Electrons have negative, holes have positive charge. Now, this is the slab of semiconductor. Let us see what is Hall effect. Statement. What is statement of Hall effect? If a semiconducting slab is placed in the magnetic field and allow it to pass a current, that means if a current carrying slab of semiconductor placed in the magnetic field, then a potential difference developed, that is potential difference perpendicular to both current and magnetic field. That is, if it is the slab of the semiconductor which is carrying a current I, it is placed in the magnetic field. The magnetic field is suppose in this direction. That is, we can indicate the directions of current and magnetic field in this way. The current is in x direction suppose, and magnetic field, applied magnetic field is in y direction. Then there is a potential difference developed within the semiconductor. That potential difference is in z direction, that is in this direction, z direction. The potential difference developed, that potential difference is called Hall voltage, that is called Hall voltage, and this effect is called Hall effect. This voltage is called Hall voltage. That potential difference is in this direction. In this direction. So, the potential difference can be developed between top surface and bottom surface. That can be measured by connecting a voltmeter. By connecting a voltmeter between top surface and bottom surface. Top surface and bottom surface. Now, what happens within the ferromagnetic within the semiconductor when we are applying the magnetic field? Let us see. This semiconductor has both electrons and holes. If we consider the majority charge carriers are electrons, in this case there are electrons. We are applying a magnetic field, then there is a force acts on the electrons due to the application of the magnetic field. That force has a certain quantity. That formula for the force acting on the electrons in the presence of magnetic field is given by force F is equal to minus B E V D. Here B is the magnetic flux density of applied magnetic field. E is the charge of the electron, and V D is the drift velocity of the electron. Drift velocity means here there is a current passing through the semiconductor because of application of certain external EMF or voltage to the semiconductor. That means drift velocity is the velocity acquired by the charge carrier, that means electrons here, in the presence of electric field. It is constant, it is steady state velocity, and it is constant for a particular applied electric field to the semiconductor. Now, in what direction the force acts on the electrons because of application of magnetic field to the semiconductors? Then we have to apply Fleming's left hand rule. So, in what way we have to apply Fleming's left hand rule? What is Fleming's left hand rule? Fleming's left hand rule. Left hand rule. What is Fleming's left hand rule? Fleming's left hand rule is used to know the direction of the force acting on the charge carrier in the presence of magnetic field. Here the current is aligned in the middle finger direction and magnetic field is in forefinger direction. Then the thumb indicates the direction of the force on the charge carrier electron. So, the middle finger in the direction of current, forefinger in the direction of magnetic field, and then thumb indicates the direction of the force on the electron. So, the force acting in the upward direction on the electrons are accumulates on the top surface like this. Electrons reaches to the top surface, then automatically there is an induced positive charge in the bottom surface, bottom region of the semiconductor slab, positive charge. So, on this negative charged electron, the force acts in the upward direction due to the applied magnetic field, that is FB. Suppose that is indicated by FB, force due to magnetic field. Now, this top surface becomes negatively charged region and the bottom surface becomes positively charged region. Then there is an electric field created between bottom surface and top surface. There is an voltage corresponding to that electric field that can be measured through a voltmeter by connecting the top and bottom surfaces. That voltage is called Hall voltage. Now, electric field creates. What is the direction of the electric field here? The direction is from bottom surface to top surface. That is called Hall electric field. What is that? Hall electric field that was created due to the force acts on the electrons in the upward direction in this Hall effect. Now, due to this creation of the electric field towards top surface, there is a force acts on the negatively charged electrons in the downward direction, because this surface becomes positively charged, then this negatively charged electron is attracted by this positive charged lower surface. So, we can say that there is a force acts on the electrons in the downward direction. That force, suppose indicated by FH. That force is indicated by FH. FH. Now, what is the magnitude of the force? What is the value of the force? What is the formula for the force acting on the electrons due to this Hall electric field? There is a fundamental formula for the force acting on the charge carrier in the presence of electric field. That is force due to electric field, that is equal to FH is equal to, fundamental formula is that charge multiplied by electric field. What is the charge here? Minus E. Electron charge is equal to minus E, and electric field is indicating as E suffix H. So, here there are two forces acting on the electron in this slab of semiconductor. They are, one is due to the magnetic field, that is in upward direction, and other one is due to Hall electric field, that force is in downward direction. Suppose upward force is more, then electrons are accumulates in the top surface, then there are no charge carriers to flow the current. If the downward force is more, then electrons accumulates in the lower surface, then there are no electrons for flowing the current. So, to flow the current, the forces must be equal and opposite. That means equilibrium state. So, at equilibrium state, both the forces are equal and opposite. So, FB is equal to FH, we can say the, what is FB? Minus BEVD. What is FH? Minus E into EH. From this equation, we can write the formula for a drift velocity VD. Drift velocity VD is equal to, so E can be cancelled on both sides, that is equal to EH by B. Now, EH is the Hall electric field, B is the magnetic flux density we are applying to the semiconductor. Now, here there is a current I passing through the semiconductor. Initially, we have taken that current can be termed in terms of current density. Now, what is current density in this semiconductor? The current density is indicated by a letter J, that is current density. current density J is equal to minus NE VD. J is equal to minus NE VD. Now, here VD is equal to EH by B, that can be taken as equation 1, and if it is equation 2, substitute to equation 1 in equation 2, then J is equal to minus NE VD means here EH by B, EH by B. This implies we can write EH is equal to what? EH is equal to okay, BJ by minus NE. Okay, this is equal to EH is equal to RH into BJ. Here what is RH? RH mathematically equal to RH RH. So, from the above equation RH is equal to minus 1 by NE for electrons. So, what is RH? From that equation, what is RH? RH is equal to EH by, what can we write? RH is equal to EH by BJ. RH is equal to EH by BJ. Now, this RH is equal to minus 1 by NE in terms of carrier concentration small n. This is for electrons. Here N is the concentration of the electrons in the semiconductor. Majority charge carriers are electrons in case of N-type semiconductor. In that case, we can take carriers are electrons. But if it is P-type semiconductor, majority charge carriers are holes. They are positively charged. The concentration of holes is indicated by P. Then Hall quotient, then RH in case of holes is equal to 1 by PE. This RH is called Hall quotient. This RH is called Hall quotient. What is the formula for RH? That is EH by BJ. EH means Hall electric field. B is the applied magnetic field, flux density. J is the current density. Here B is applied field, that is known value. Suppose EH, we cannot measure EH directly. J, current density, we cannot measure current density directly. Then how can we determine the Hall quotient? How can we determine Hall quotient? That means determination of Hall quotient. Determination of Hall quotient, RH. Experimentally, how can we determine Hall quotient? What is the formula for Hall quotient? We have RH is equal to EH by BJ. What are the fundamental formulas for electric field and current density? So, electric field EH in terms of voltage, that is equal to VH by certain distance between positive and negative charges. What is that distance? If we go to previous page, okay, taking this distance from positive to negative, this distance is taking as W. and this is taking as a T. Okay. So, EH is equal to VH by W, and T is the thickness, W is the width. Then area of the cross section of the semiconductor slab is equal to W into T. Area of the cross section is equal to W into T. So, this is W. Now, what about current density? Current density is defined as amount of current flowing through the semiconductor per unit cross sectional area. So, amount of current flowing through the semiconductor per unit cross sectional area. Current divided by cross sectional area. Cross sectional area means already thickness multiplied by W. This is the cross sectional area of the semiconductor slab, and that means W into T. Now, substitute these two expressions in this equation RH. Okay, then RH is equal to EH means VH by W divided by B as it is, and J I by WT, that is equal to VH divided by B W I WT, we have to write in the numerator WT. So, W cancel, then RH is equal to, that implies RH is equal to finally VH into T by B into I, VH into T by B into I. So, by using this formula we can determine the Hall quotient. How? VH can be measured in the voltmeter directly. So, we can substitute that value in the formula. Next, I value also we can measure directly. Amount of current flowing through the semiconductor can be measured directly by connecting the ammeter to the circuit. And next, what are there in this formula of Hall quotient? VH can be measured directly and I can be measured directly. Thickness T of the semiconductor slab, this can be measured by using a screw gauge or a vernier calipers depending on the thickness value. And B is applied field, that is known value. Now, why we have to discuss about Hall effect? Why we have to know about Hall effect? Because it has a very important applications. That's why we have to learn Hall effect. What are the applications of Hall effect? Applications of Hall effect. Applications. First application. Once we determine the Hall quotient, that means RH. Okay. What is the formula for Hall quotient? Minus 1 by Ne. Once we determine the Hall quotient, we know very well about charge of the electron E. Then we can estimate, we can determine N value. N means concentration of the electrons. If it is p type, we can determine concentration of the holes. So, carrier concentration of semiconductor can be determined by using Hall effect. What is the first application? Carrier concentration. Carrier concentration can be determined First application. Next, second application. If we determine Hall coefficient, if it is positive or negative, then what can we say? If the Hall coefficient is negative, then that semiconductor is a n-type semiconductor. N-type semiconductor. If Hall coefficient is positive, then that semiconductor is a p-type semiconductor. If it is positive, then that is a p-type semiconductor. How can we say in case of n-type semiconductor, majority charge carriers are electrons. Electrons have negative charge. That's why we are getting Hall effect as negative for n-type semiconductors. But in case of a p-type semiconductor, the majority charge carriers are holes. Holes have positive charge. That's why we are getting positive sign for Hall coefficient. Next, third application, very important, that is we can determine the mobility, very important factor for the semiconductors and conductors. So, that is mobility. Mobility of the charge carrier can be measured. Mobility of charge carrier can be measured. What is the term for mobility? Mu, indicated by mu. We know very well that sigma is equal to Ne mu. That implies mobility mu is equal to sigma by Ne. 1 by Ne is equal to mathematically RH into sigma. So, once we determine the Hall coefficient, conductivity is a constant value, then we can determine the mobility of the charge carrier, mobility of the electron, mobility of the holes. Mobility means how much it has fast, how much it is fast, the charge carrier in this semiconductor. That way mobility can be determined. Fourth application. So, in case of a formula, RH is equal to VH T by B into I. Once we determine the Hall coefficient, okay, B is known value, we can determine Hall coefficient. If we take unknown magnetic field that is applied to the semiconductor and doing this Hall effect, then we can estimate the unknown magnetic field B value by using this formula once you determine the Hall coefficient. So, fourth application is we can determine unknown magnetic field, flux density B. Okay, thank you.